Continue my series on this year, that is in 2025, this year's IMO problems. So yesterday, I think one a day is probably enough for me, but yesterday I got through question one. Um, I know very little. I've been deliberately trying to find out as little as possible about the papers, but I think, heard that question six is hard, and I think that probably means it's a bit risky to try and make a video of it. But I may do, but it might just end up being a video of me thinking about it for a while and having a few ideas, but not actually solving it. Um, and I also had some indication that question two is a geometry question, and I just don't really feel like doing a geometry question in real time. I've not ever sort of practiced those, and in common with many people, I don't really enjoy those. So I'm going to have a quick look at question two now. If indeed it's a geometry question, then I think because the questions are supposed to be, I believe, on each day, the first question, they sort of get harder as so question one mod three is sort of supposed to be not that bad, and then question two mod three sort of medium, like mother bear or something, and then question three mod three is the really interesting one. Although again, the rumors are that question three on this year is actually not as hard as a third question on the paper. Usually is. But I think I want to sort of try and do these questions in rough order of likely difficulty. So I think I might, if question two turns out to be a geometry question, I think I shall skip to question four. And then I have a personal reason for being interested in question five, which is that I know the person who who set it and had it, was very pleased to have it selected for the competition. So that would be my plan for the third question I'll try, but let's not look too far in the future. So I'm now going to check this whether problem two is indeed a geometry question, in which case I'll just jump straight to question four. So I'm just having a quick look now. Yes, it's sort of to do with circles and radiuses and lines and things, so I'm going to skip that and head for question four. And just a quick glance at that. Does that look like it hasn't opened up yet on my screen? Now it has. Okay, this looks like a sort of elementary number theory question. I won't look at it just yet because I want to share my screen first. And then once I've done that, I'll have a look at the question. So there's my rough paper in inverted commas. And now let me read the question and then write it down here as well. So a proper divisor of a positive integer n is a positive divisor other than n itself. So perhaps I won't bother to write that down, but so that's a fairly natural definition. So the infinite sequence A1, A2, blah, 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 consists of positive integers each of which has at least three proper divisors. It doesn't say that one is not a proper divisor. So I suppose I will. But having said that, I don't know whether one would normally count. I'll have to see what to what extent that makes a difference. So it sounds as though having at least three proper divisors is equivalent to having at least four divisors full stop. Now, what else does the question say? So for each n greater than or equal to 1, the integer an plus 1 is the sum of the three largest, goodness me, what a strange sequence, proper divisors A. Now, what's the question going to be? Determine all possible values of A1. Gosh, that's nice. A nice clean question. Determine all possible values of A1. And now let me hide the page that's, I'm going to close the page because I like to be very safe about not accidentally seeing the solution. Well, in this case, it was okay because the solution was a video solution, so not much danger of accidentally opening a video. Right, so there's a question that immediately occurs to me here. So question one, are there any possible values of A1? So let me just think about what could go slightly wrong. So what could go wrong is that you follow this procedure of summing the three largest proper divisors of the previous number, and at some point you find that you've run out of divisors. You don't have three proper divisors anymore. Now, I don't know how this happened, but I've already seen that the answer to question one is yes, because if I take a reasonably large, say, power of 2 or something like that, then it'll have divisors themselves be, oh, wait a minute, is this going to work? This is actually not completely obviously going to work. So let me just have a go at, so let's try the smallest possible number. I'm writing this down with 3 proper divisors. I'm writing that down just because I want to, whoops, that's missing an S. Because I want to emphasize I'm using a rather general problem-solving technique. Let's just try the minimal thing that's not completely ruled out. And it would be completely ruled out if it didn't even have 3 proper divisors. So what's the smallest number with at least 3 proper divisors? I think it's 8. So, because 8 has the divisors 1, 2, and 4, and I don't see how one's going to do better than that. Maybe what about 6? 6 has 1, 2, and 3, actually. So I sort of like 8. Or do I? 8 seems to fail. I'll try 8, and then I'll go back and try 6. So I think I see what's happening with 6. So 8, the 3 divisors are 1, 2, and 4. Those add up to 7, and then the sequence terminates. Because 7 does not have 3 proper divisors. But 6 actually is interesting because it's a fixed point. So 6 goes to 1, 2, 3. Add those together, we get 6. So the answer to question 1 is yes. We can take A1 to be 6. So that's a small amount of progress. It's very, very tempting at this point to make a sort of ridiculously bold conjecture that A1 has to be 6. So I'm going to ask that. Can A1 be anything other than 6? And I think I've just seen something that's annoying that I don't have a sort of, it just flashed into my mind, and when it flashes into my mind, that's exactly what I'm trying not to do with these videos. But I think I can actually sort of perhaps do a sort of reconstruction of this, of whatever was going on unconsciously in the back of my mind here. So supposing I take a number that's a multiple of 6, like 6m. So what are the 3 largest proper divisors, well, I can divide it by 2. Hmm. This is not absolutely going to work, but it might work. So let's just, it might work at least for some values of m. So I know that 3m will be the largest proper divisor because it's all divisors are going to be 6m divided by something, and the smallest thing we could divide by is 2. And likewise, the next biggest has got to be 2m. Now, if m is not divisible by, or if 6m is not divisible by 4 or 5, then the next biggest one will be m. And so that's if 4 does not divide 6m and 5 does not divide 6m. And so that will give us, when you add them together, 6m. So the answer to question 6, sorry, the answer to question 2, I mean, is yes, it can be anything other than something other than 6. For example, if we take m to be a prime, a large prime, let's say, then 6m will not be divisible by 4. In fact, for 6m not to be divisible by 4, we want m to be odd. So the conditions that we need are m is odd, and 5 does not divide m. If it satisfies those two conditions, then its 3 largest divisors will be 3m, 2m, and m, and those will add up to 6m. That's actually starting to look a little bit promising. So I've now got a class of, so what was the technique that led to that? So sort of, let me just say general technique. Not right today. General technique. Given an example, try to use it to build more examples. That's a sort of very general thing one often tries to do in mathematics. We have an example. Have we got any example preserving operations that we can use to build new examples out of old ones? And a pretty natural thing to try in this context is just multiplying everything by some factor. Because, so I think the thought that went into my mind was that if 1, 2, and 3 divide 6 and the other 3 largest divisors, then there's a sort of reasonable chance that m, 2m, and 3m are the 3 largest divisors of 6m. And indeed, that turns out to be the case for a large collection of m's. Now, what else can we say? Well, actually, I think we can start to say a bit more than this, because I think there's a reasonable chance. So question 3, I have a lot more faith in this question. So question 3 is that everything? And I think the answer may very well be yes. And I want to make some observations. We want the 3 largest divisors. Now, if there are only 3 largest divisors, then on average, they've got to be at least as big as m over 3. If on average they've got to be at least as big as m over 3 and they're all different, then we've got to include m over 2. So, sorry, we've got to, sorry, I'm being a bit confusing here. So when I say m here, I mean the number m and not number 6m. So let me just be less confusing about that. So let me just, so let n, so n was 6m above. So let n be a positive integer. Actually, sorry, I realize that I'm now, I've accidentally strengthened the requirement on n, which is that it should be a fixed point of this operation. So I think I'm about to characterize fixed points, but not all possible A1s. So that said, I think that's still going to be useful. So let me just do that first. So question 4, for which A is FA equal to A, where FA equals sum of 3 largest divisors of A. So that was the question I was asking. I'd forgotten that that wasn't the original question. So, but I think it's going to be worth answering that question. So, what I've just shown is that so if the divisors are D1, D2, D3, then D1 plus D2 plus D3 equals A. So let's make it D1 greater than D2 greater than D3. So D1 is greater than A over 3. So D1 actually equals A over 2. So D2 plus D3 equals A over 2. So D2 is greater than A over 4. So D2 must be A over 3. So D3 equals A over 6. So we must have that A is a multiple of 6, and we've already up here added the extra necessary conditions that it must be an odd multiple of 6 and it mustn't be a multiple of 5. So the answer is we've already characterized those. So just quickly write it down. So the answer, 6 divides A, 12 does not divide A, and 5 does not divide A. Those are the conditions that give us that f of A equals A. So now another natural question. If A is not a fixed point of this function f, can A1 equal A? So one way this might go if we were lucky, so I think I'll put this down as a little conjecture. Question 6. Well, there are two questions I have in mind. So one way in which we could imagine this failing is if there's a, is it possible that f A does not equal A, but f of A equals f of A. In other words, we start off with something that's not a fixed point, but once we do this operation once we take the 3 largest divisors and add them together once, then at the next step, we do hit a fixed point. So for example, could there be a number other than 6 for which the 3 largest divisors add up to 6? If so, then that would give us another choice for our A1. So I'll come back to that question in a minute, but I also want to note down another question. So this I wrote down as perhaps the simplest way in which the answer to question 5 could turn out to be yes. And question 7, with an eye to how one might end up being able to prove that a number is not, or to prove that a whole large class of numbers, because at the moment I have this sort of thing, if I've got a really large number, how do I know that when I sort of take the sum of the 3 largest divisors and then do that again and do it again and do it again, I won't sort of suddenly, after a few steps, hit a number that is very nice. It's one of our fixed points, and I may have to look for some sort of invariant at some point. But question 7, what was I going to ask? I had a question very much. Oh, yes. If A is not a fixed point, in fact, I think I already know the answer here. Perhaps I'll just write it more concisely. If f of A does not equal A, must f of A be less than A. So if we could somehow show that except with fixed points, we have a decreasing sequence, then we'd be in great shape. However, I think we sort of already know that we don't necessarily have a decreasing sequence because of that phenomenon about not wanting n to be divisible by 4 or 5. So if n is divisible by 4 or 5, then it's going to go up. So let's have a look at a counterexample to that. So the answer to this is no, but let's actually look at what happens. So let's look at the number, the simplest number I can think of that violates this condition but is a multiple of 6 is 12. So I'll just take, I suppose I could take, yeah, no, 12 looks like the smallest. So let's see what happens with 12. So 12, if I add the 3 largest divisors, those are going to be 6, 4, and 3, which gives me 13. So it's bigger than 12. But 13 is in deep trouble. So terminates. So let's have a look at some more and see whether we can. So let's go for 24, just out of interest. So 24 is going to go to 26, which does not have 3 proper divisors. Well, actually it does. It's got, if we count 1, so it's got 1, 2, and 13. So that gives us 16, and that gives us 8, 4, and 2, so 8, 12, 14. This is in deep trouble, I think. So now there's 7, 2, and 1. That's 7, 9, and 10. 5, 2, and 1. So that's 7, and it goes to 8. And finally, 1, 2, and 4 goes to 7. But notice something, I mean, we had to go several steps, and how did we know that we weren't going to hit, say, 6 at some point, or so let's just try just to get a bit more feeling for what's going on here. Let's try a number that's divisible by 5. So we want it divisible by 6 as well. So the simplest one will be 30. What happens with 30? So the 3 largest will be 15, 10, and 6. So that gives me 31. So that's another example where it has gone up in the first instance. And then it terminates because that has not got 3 proper divisors. Okay, so the question started to get interesting at this point. We have to decide. Now, it is interesting also that although it can go up, it has to satisfy some rather particular conditions in order to go up. So could we argue, for example, that the something like that the number of, well, the sort of multiplicity of 5 in the prime factorization can't go up and things like that. Or could we argue that if you're not a multiple of 6, actually that's a promising idea. So once you're not a multiple of 6 anymore, we never in the sequence have another multiple of 6. So perhaps we could think about that. So question 8. So I remember I was wanting an invariant. And why did I think of this invariant about being a multiple of 6? Well, it is right here. It's a necessary condition. So although we don't necessarily go down. These examples show that we don't necessarily have to go down when we apply the operation f. We do seem to have that we've lost the property of being a multiple of 6. On the other hand, actually, I can see already that that's not going to work in general, because I could just, by the usual trick, I can multiply these examples by, say, 6, and then what I'll get on the right-hand side, I mean, what I'll get when I apply f will also multiply by 6. So let me just write that question, since I did briefly ask it to myself. If fa is greater than a, can fa, or can any iterate of f be a multiple of 6? And this was not a great question, and the answer, because the answer is yes. And let's just quickly give an example. I said we could just multiply this by 6. So let's say, e.g., 72. I probably don't have to multiply by 6. I could probably get away with something like 48, but what are the 3 largest multiples, divisors of 72 there? That goes to 36 plus, if I divide by 3, I get 24, and if I divide by 4, I get 18. 36 plus 24 is 60, so this goes to 78, which is, as we expected, 13 times 6. Let's just see what happens if I pursue this 78. So 78 goes to 39 plus, and then 78 divided by 3 is I'm going very slow suddenly, 26. 78 is not a multiple of 4 anymore, so we lost that property when we multiplied by 13 over 12. We just got rid of a whole nice bit of factorization. And so I think this is actually giving us some useful clues. What's the next largest factor of 78? So we've got 13, it's 13 times 6. So we have 13 times 3, 13 times 2. Help, is it going to be 13 times 1? I have a weird feeling it is, because 78 is not divisible by 5, wherever it is. It's not divisible by 5, and it's not divisible by 12. So equals 78. So actually, it is possible that f of a, that a is not a fixed point, but f of a is a fixed point. So 78, sorry, 72 was our example of that. So I think we may be closing in on something, but what exactly is not so clear. I'm interested in other forms of behavior that might or might not be possible. I think I just want, because this could be a very, very useful lemma, I want to consider another question, which is, can you, if you don't have a multiple of 6, can you ever get to a multiple of 6? That seems to be something that would be worth. But if 6 does not divide A, can 6 divide f of A? I want the 3 largest divisors of a non-multiple of 6 to add up to a multiple of 6. I don't really see a reason for that not to be possible, which is a bit distressing. because then the question starts to become truly mysterious. I wonder if I just try some randomish number. If I just try 15 or something, this is really silly, but I'll just try 15. So what are the three largest divisors there? 5, 3, and 1. And that adds up to 9, which is not quite what we wanted, but it's... Aha. So a quick observation is that if the number is odd, then the three divisors will have to be odd. So that's actually also potentially helpful. So for 6 to divide f of a, we need a to be even. So now let's think about, so in fact, even for 2 to divide f of a, let's just make that clear. What about a condition for 3 to divide f of a? So it would be nice. Do we need 3 to divide a? That seems a bit more optimistic somehow. What if I try and take 2 prime numbers, both of which are multiples, both of which are 1 mod 3, and take their product, because then I'll have 1 plus p plus q, which will be 0 mod 3. So I will try that. So what's the simplest example? You could take 7 and 13 or something like that. So 7 times 13, which is the famous not quite prime number 91. What are its 3 largest divisors? They are, I believe, 13 and 7 and 1. And that equals 20, 21. So I have a number that was not a multiple of 3, but when I took f of it, I got a multiple of 3. So what happens if I double that? So 182. So its largest. I see now we have a slight thing. So we get 26. This is quite interesting that I think this is not quite going to work. So 26 plus so I think the next largest will be 14, but the next largest is not going to be 2. There's just multiplying everything by 2 doesn't multiply this by 2 because we get 13. That's another one. I think those are the 3 largest. I haven't actually checked that super carefully. But assuming that's okay, we have 26 plus 14 is 40, 53, and we get that it terminates. So I do not actually yet have an example. I do have an example where I can't prove it like this. I can't prove that because 3 divides f of a, then 3 must divide a. But maybe I can still prove that if 6 divides f of a, then 6 must divide a. So let's think about that. We've got a equals d1 plus d2 plus d3. A is even. We've already established that a must be even. So d1, I'll again assume that they're decreasing. So d1 equals a over 2. Sorry, a doesn't have to equal d1 plus d2 plus d3. What I want is 6 divides d1 plus d2 plus d3, and d1, d2, and d3 are in decreasing order the largest factors of a. So d1 is a over 2. Um, is there any reason that D2 and D3, when added to D1, couldn't be, or when added to A over 2, couldn't give us a multiple of 6? And so we also have that A is not, we're assuming this, not a multiple of 3. So A over 2 is not a multiple of 3. I don't see any reason for this not to happen, so I think I'm going to try and find an example. I'm not quite sure I see a way of looking for an example other than, well, I suppose uh, so if D1 is A over 2, is there anything else I can say? If A is even, then um, I want to know, I'm just trying to think what that tells me about the relationship between D2 and D3. So for example, if D1 is also even, then so if A is a multiple of 4 at the same time, then one of D2 and D3 are going to have to be A over 4. Okay, so let's just, I'm going to make a little note here because I've got a lemma. I don't know whether it's going to be helpful, but if 4 divides A, then we cannot avoid, so then D2 or D3 equals A over 4, just because the absolute smallest that the third largest factor can be is A over 4. And so if we've got an A over 4 that divides, that is a factor, it's got to be one of the three largest. So let's assume that D2 and D3 are not necessarily in order. So let's make it D2. So then say D2, but I've dropped, I say, the assumption that D2 is bigger than D3. So that wouldn't be without a generality. So then D1 plus D2 equals A over 2 plus A over 4, which is 3A over 4 is a multiple of 3. So since 6 divides D1 plus D2 plus D3, we must have that, so that D3 is also a multiple of 3 because it's, so 3 divides D3, which implies that, so since 3 divides one of the factors, we get that 3 divides A. So if 4 divides A, then 3 must divide A, contradicting this assumption. So 4 doesn't divide A. Can we do something similar to that in general? If 4 does not divide A, does that help us at all? Actually, we were assuming that 3 doesn't divide A, so we could actually have said that D2 was indeed the next largest factor. I mean, that A over 4 was the next largest factor. We are not necessarily assuming that 5 doesn't divide A. So if 5 does divide, oh, actually, so if 4 doesn't divide A, then that means that 12 doesn't divide A. So we have this condition here. We've got that 12 doesn't divide A. And let's just go back to here. What are we doing? We're assuming that, what's the question we're trying to answer? If 6 doesn't divide A, can 6 divide f of A? So I've slightly lost my thread for a second. What was I in the process of doing? So I was taking an A that is not a multiple of 6. We've got that it must be for f of A to be, and we're assuming that yeah. So we're trying to argue, say A is not a multiple of 6, but 6 does divide f of A, and we want to know what can we say. And the facts that we've got so far are that A must be even and that 4 does not divide A. So I'm actually going to consider the situation, consider whether 5 can divide A. We also know, of course, that since 6 doesn't divide A, we have that 3 doesn't divide A. So what about considering whether 5 divides A? But I won't put that in a line. So these are things we absolutely know. Here's one that we're not so sure about. Can 5 divide A? So if 5 divides A, because it's even, then we'll have that, and 4 doesn't divide A and 3 doesn't divide A, then we'll have D1 equals A over 2, D2 equals A over 5. And then we need A over 2, so we need that 6 divides A over 2 plus A over 5 plus D3. And A over 2 plus A over 5 is 7A over 10. Which doesn't look particularly problematic. So let's take A equals 10R. So then our numbers are 7R plus D3. We want 6 divides 7R plus D3, and D3 must be the next largest factor after A over 5. And A was equal to 10R. So what might D3 be? We don't want D3 to be, so we've got 5R and we've got 2R. We don't want D3 to be R because 5R plus 2R plus R equals 8R. And if 6 divides 8R, that tells us that 3 must divide R, in which case 3 must divide A, so that won't work. So D3 should not be a multiple of R, but that's starting to look slightly difficult. So if I have a factor of 10R that is not a multiple of R, but is bigger than R, that's starting to look exceedingly hard. So I have a factor that is strictly between R and 2R. Perhaps it's not impossible. So that's strictly between r over 10 and r over 5. So what about something like r over 7? So what about if I take a equals 70? Or something like that. This is just something that may not work, but what are the three largest factors of 70? They are 35, and if I divide by 7, I get 10, and if I divide by 10, I get 7, but were those the largest ones? So the small factors of 70 are 1, 2, 5, so 1, 2, 5, and I've divided by 1, 2, 5, and 7. So if I divide by 2, I get this. If I divide by 5, so I'll skip something here, I get 14. And if I divide by 7, I get 10, which does not, unfortunately, give me a multiple of 6. So 70 didn't work. Are we on to a more general pattern here? And so something actually that happened there, S wasn't between R and 2R, it was actually between 2R and 5R, so that's also possible. There's nothing to stop that happening. So let's just think about what we can say about the largest factors. So we know that R mustn't be a prime, because if R is a prime, then the three largest factors of A will be 5R, 2R, and R, which will give us 8R, which is not a multiple of 6. I'm assuming R is not 3. Actually, if R is 3, something's a bit odd. So if R is 3, we just got something. We've looked at 30. What happens to 30? And it gave us 31 or something like that. So that just was a non-example. So let's suppose that T be largest proper factor of R. Perhaps I should say what the general question I'm thinking about here is. The question, where have we got to? Question 10. What are the three largest factors of 10R? That's the question I'm addressing now. So it seems useful to know about the factorization of R. So if T is the largest proper factor of R, then some candidates for the largest three factors are 5R, 2R, and then and R is another one. But we can also get things by taking a factor of T. So we can get, for example, 10T, and we could have 5T. We couldn't have 2T because 2T is smaller than 5T and 10T and 2R. So I think these are the only possibilities, and we don't know quite what order they're going to come in. I think it's possible for 10T and 5T to be bigger than 2R, but 10T plus 5T is a multiple of 3. So if those 2 and 5R are the three largest factors, then that would tell us that 5R had to be a multiple of 3 because the sum of them has to be a multiple of 6. And so for 5R to be a multiple of 3, R would have to be a multiple of 3, but R is a factor, and that would give us a 3. divides A, which we know is not the case. So 5t cannot be one of the three largest factors. So let's get rid of that. So actually, we've narrowed things down quite a lot. We've got 5r, 2r, r, and 10t. That's whatever the three largest of those are. We also know that t is not r over 2 because we've also ruled out a being a multiple of 4. So t is less than or equal to r over 3. R is not a multiple of 3, so in fact, t is less than or equal to r over 5 because it can't be r over 4 either because 4 does not divide a. So t is less than or equal to r over 5. And if t is less than or equal to r over 5, then 10t is less than or equal to 2r. But we don't know that it's less than or equal to r. In fact, we had an example where it wasn't. And if 10t equals 2r, then of course it's not going to be a distinct largest factor. So I don't know whether actually in the question it's not absolutely clear whether. No, so I was about to ask something, to say something slightly meaningless. So where are we now? So could t be r over 5? So if a equals 10r, I think I want to try that. So let's try a equals 50. I've just chosen that to make, to be the simplest example where r actually is a multiple of 5. So the largest factors of 50 are 25. That's if I divide by 2. If I divide by 5, I get 10. And if I divide by 25, I get 2. So that equals 10 times 5, so r equals 5. I've also got 5 as a factor. So 10 was duplicated in this case. So this is not going to be a very good example. Plus 5 equals 40. In general, if t equals r over 5, then this 10t equals 2r. So it looks as though we're forced into 5r, 2r, and r. So we know that can't be the case. What if t equals r over 7? So let's just think about it like this. We have that if t is yet smaller, but bigger than r, we will need 7r plus 10t. 6 divides that. And note that t divides r. So if t was r over 7, that would be equal to 49t plus 10t equals 59t, which would then tell us that 6 divides t and then 6 divides a, so that's no good. It can't be 8 and it can't be 9. So I seem by a rather horrible case analysis, I think by a horrible case analysis, I have ruled out all possibilities. Just for, unfortunately, one rather small thing. I think I've shown that A can't be a multiple of 5. But I'm still not quite seeing something, I think. Perhaps I should just think, do I really want to spend more time on this question? I think possibly I do. So I'd be interested to know, for example, question 11, just I want to try and find a counterexample to that. So can we have D1, D2, D3 being the set 0, 1, 2, mod 6 or something like that? Oh, that's what I mean. That's not what I mean. Let's go for something like 0, 1, 5, mod 6. So any reason that we couldn't have the largest factor being, no, I don't want a multiple of 6, sorry. Let's go for 1, 2, 3 mod 6. So that would tell us that let's consider the case where we have some 3 prime numbers. So let's have A, because I'm asking an even more specific question. Can we do this if A equals product of 3 primes? I don't know why I want 3 primes even. Perhaps I could have 2 primes. Let's try 2 primes first of all. So just the reason I've chosen something like this is that it makes it much easier to say what the 3 largest divisors are. So those are proper divisors. So then that would tell us that we want, what are the 3 proper divisors? They are P1, P2, and 1, I believe. Which doesn't look very difficult somehow. I can, what is it? Actually, it's not as easy as all that because they're supposed to be prime numbers. And if we, so the only numbers that are co-prime to 6 are 1 and 5, and I can't make 6 using 1s and 5s here. So actually the answer is no, I think. Except if I take P1 to be 3, say, and P2 to be 5 mod 6. Let's just quickly try that. So P1, because 3 is the one multiple of 3 that is a prime. I suppose I could consider also a case of P's, one of these primes being 2, but then the other one will have to be 3, and that'll make it 6. So I'll have P1 equals 3, P2 equals 5. I've already tried 5. Oh yes, wait a minute. So if P1 is 3, then P2, in order for 3 plus something to be, P2 would have to be 2. Yep, so no except if A equals 6. So that seems actually quite an interesting case to note. And in fact, I think that could be very relevant because maybe we can do something like looking at the largest two prime factors. But let's just also try just to rule this one out as well. What about A equals P squared for prime P? Then we have the largest factors are, oh well, that hasn't got, that doesn't work, that hasn't even got 3 proper factors. One more case that I wanted to, so I will go to the case of 2 primes. I mean, sorry, a product of 3 primes with P1 greater than P2 greater than P3. So now I know that A over P1 is, well, sorry, the biggest one will be A over P3. So I get P1 plus P2, sorry, P1 times P2. What other factors have I got? So I've got products of 2 of them, and then I've got products of 1 of them, and so it's going to depend a little bit on things like, is P2 times P3 bigger than P1? Let's assume that P2 times P3 is bigger than P1. So I'll put that little assumption over here. In which case, oh, P1, P3 is certainly bigger than P2. So because P1 is already bigger than P2, so P1, P3, and P2, P3. So is it possible that the sum of those is a multiple of 6 in some non-trivial examples where these are just not things like, they don't include 2 or 3. So we want P1, P2 plus P1, P3 plus P2, P3 to be a multiple of 6. Is there anything that stops that happening? I don't really see an obvious obstacle, but perhaps there is one. Let's assume that each of P1 and P2 and P3 are either 1 or 5 mod 6. So that's the sort of case where we're trying to rule out 2 and 3. So if they're all 1, that's no good. So at least one of them has to be 5. If they're all 5, that's no good because I'll still get 1 plus 1 plus 1 mod 6, which will give me 3. So that's no good. So at least 1, 1, and at least 1, 5. So without loss of generality, P1 is 1 mod 6. P2 is congruent to 5 mod 6. So I get 5 plus R, and then 1 plus 2 mod 6. P1 plus P2 mod 6 is 0, so 5 plus 0 mod 6. And it doesn't work. This is getting sort of strangely conspiratorial seeming. How is it that it's proving to be so hard to create a multiple of 6 when we don't start with a multiple of 6? I'm starting to think that it is actually impossible. So let us now, in general, if A equals P1 to the R1, P2 to the R2, let's say D to the RD, with P1 greater than P2. So if we've got the prime factorization looking like that, then what can three largest proper divisors, well, right, proper, but I mean, what can they be? What are the possibilities for that? Because I seem to have been sort of driven in that direction. So D1, the largest one, has to be A divided by the small. Actually, that's going to be more convenient, isn't it, to have these going in increasing order. Because the largest divisors will be the ones where I divide by the smallest prime. So I'll make those come near the beginning. So D1 has to be, I'm assuming, of course, all the Ri's are strictly greater than 0. So D1 has to be A over P1. What about D2? Well, there's a competition between two possibilities. So it's going to be the maximum of A over P2. That would be the next obvious one. Or A over P1 squared. Because I'll just quickly justify that. So the only thing I can divide by that would be smaller than, or potentially smaller than P2. I can't, there'd be nothing that involves P3 or beyond, nothing that involves a higher power of P2, so it has to be a higher power of P1. So P1 squared, since we've already got A over P1, that's the most that we could do. I feel as I should have done something more systematic like this much earlier, but never too late. What about D3? Let's try and be systematic in the same way. So we know that it can't involve anything from P4 onwards, because then I might as well just divide by P3. So A over P3. Could I? So it could be A over P2. Okay, so this is slightly complicated to write down, actually. So if we chose A over P2, then A over P2 won't be what we have here. But if we chose A over P1 squared, then it could be A over P2. So unfortunately, it splits into cases. So instead, I'm going to say D1, D2, D3 equals, or let's put it as in, make it an ordered set, because that's kind of what it is. So the possibilities are A over P1, A over P2, A over P3, that's the most obvious, or A over P1, A over P2. So if we've got A over P1, A over P2, then the only thing that could be larger than A over P3, it's possible that both A over P1 squared and A over P2 squared are larger than A over P3, but then A over P1 squared is larger than A over P2 squared. So we get A over P1 squared. So that's it for A over P1, A over P2. So what else happens? We could have A over P1 and then A over P1 squared and then A over P2. That's another possibility. Or we could have A over P1, A over P1 squared, A over P1 cubed. I think that's it, because I can't get as far as a over p1 a over p2 squared, because that's smaller than all of these three numbers automatically. And therefore, yeah, those are the four possibilities for D1, D2, and D3. All right, so can any of these things, so actually what's nice about this is that it's completely general. I'm not making any assumptions about A, except that it has a prime factorization and it's got enough prime factors for these numbers to exist, or one such triple to exist. Now, A over P1, A over P2, A over P3 equals A over P1, P2, P3 times P1, P2, P1, P3. Sorry, let's write it in the order which I've. So P2, P3, P1, P3, P1, P2. And when we add these together, we've already seen in this case here, in the argument here, that we'll have to have we will not be able to do it without having either P1 equals, I mean, one of the primes being 2 or one of the primes being 3. And I suppose I didn't quite, I think we've sort of basically dealt with the case where yes, we know that actually we can somewhere earlier on I said that we can, yes, we know that A must be even. Just to check, this was the question: if 6 doesn't divide A, can 6 divide f of A? We know that if it does, then A has to be even. So actually, I could have added in here P1 equals 2, and it might simplify a little bit the calculations. So that's A over 2, A over P2, A over P3. And so actually that cuts down the possibilities really quite a lot. So if P1 equals 2, then this is equal to A over 2, P2, P3, which I don't care so much about. P2, P3, 2P3, 2P2. And when I add, so 3 does not divide A, so 3 doesn't divide this, so we need that 3, and also 4 doesn't divide A, so we've established that as well. So this thing is odd, so we would need 6 divides P2, P3 plus 2, P2 plus P3. Is that possible? Without, we don't want to allow P2 or P3 to be 3 mod 6. So actually 1 or 5 mod 6. If they're both 1 mod 6, then we'll have 1 plus 4, which makes 5. Similarly, if they're both 5 mod 6, we'll get 1 minus 2, which is minus 1. Wait a minute, they're both 5 mod 6. We get 1 minus 4, which is minus 3, but anyway, we don't get 0. So if one of them's 1, the other one's 5, I get 5 plus 0. Same sort of argument. So that does not work. And that rules out this case here. So now we have some other cases. Yeah, that's a little bit, at least there are only 4 cases. And also we've also got that P1 is 2 now. So what about A over 2, A over 4? I feel sort of dealt with this actually. And then A over P2. And this is a multiple of 3. So this would have to be a multiple of 3, which means that A is a multiple of 3. And that we don't want. In fact, if we have a over p1 and a over p1 squared, in other words, a over 2 and a over 4, that's always going to be a problem. It'll force a to be a multiple of 3, which then makes it a multiple of 6. So I think I do actually have a proof. There was this slightly subtle step here, but what have we? It's not a proof of the whole question, but it's a proof of something that seems extremely promisingly. So we've answered, the answer to this question is no. So what now? Um, how would I guess things are going to carry on from this point? I want to guess that if A is not a fixed point, then when you apply the operation F, the multiplicity of 6 as a factor of A, so A is 6 to the K times something that's not a multiple of 6, that should probably go down. Let's go back and look at some of the examples we had here. So for example, here the multiplicity of 6 was 2 because it's 2 times 6 squared, whereas here it was just 1. It was 13 times 6. And then if we, but then it was a fixed point, so it's not a counterexample to what I said before. It's still going to be, seems as though it's going to be a little bit difficult to describe the A's that land us on the fixed points. But we've characterized the fixed points. So I think actually the next question I want to ask, let's just store away the lemma that we just have here, which I, and also the information about what the 3 largest divisors can be. And at this point, I would like to see if I can characterize those numbers A for which f of A is a fixed point, but A is not a fixed point. So I need f of A to be a multiple of 6, but not a multiple of 5 and not a multiple of 4. We know we have one such example, which was 72, because that was a multiple of 4. So I feel as though I should be staring at this a bit more and seeing what it tells me. So in fact, we could even calculate what f of A is. I've worked out what the 3 largest divisors are. But now I can't necessarily assume that A is... so next question. So this, going back to this idea of trying to create a decreasing sequence, let's have a look at question 16. If 6 does not divide A, is FA less than A? Unfortunately, I think I may have a counterexample of that up above. Let's go and have a quick look. Oh no, all these counterexamples were multiples of 6. So 15, for example, was not a counterexample, I think. I think the answer is going to be yes. So we can actually have a quick look at this here. So if 6 is not a multiple of A, then P1, P2 it can't be the case that P1 equals 2 and P2 equals 3 in the prime factorization. So P2 is at best 5, and P3 is at, I mean, the smallest it can be is 5, and the smallest it can be is 7. So over here, a half plus a fifth plus a seventh is smaller than 1. And a half plus a quarter plus a fifth is also smaller than 1. And then this is going to be, what's the difference here? That is amusingly actually equal to this. I seem to have written the same thing down twice. And that was just in the case where the ordering was the other way around, but it's still the same 3 numbers. And then this is worse still. So it's it's a half plus a quarter plus an eighth, which is still less than 1. So the answer is yes. So that's actually very useful. So we get that A1 must be a multiple of 6. So proof, if A1's not a multiple of 6, then by the slightly complicated argument that we had here, then A2 is not a multiple of 6, and therefore A3 is not a multiple of 6, and so on. So nothing's a multiple of 6. But if nothing's a multiple of 6 and it decreases all the time, then we have a decreasing sequence of positive integers, which won't do. So we've made some definite progress here for a whole class of numbers that it cannot be A1. So let's write A1 equals 6m as before. So now we have that D1 equals m over 2, sorry, equals 3m. D2 equals 2m. And we must have that A2 is a multiple of 6. What are the possible values of D3? Quickly go back to here. There are not very many possible values of D3 actually, because it's got to be either P3, but in order to be P3, P3 has to be bigger than P1 squared. And then so D3 equals, so I've divided by 2, I've divided by 3. So I could divide by 4, so that's 3m over 2, or I could divide by 5. Or I could divide by 6. And there aren't any other possibilities, are there? I don't see how there could be any other possibilities. Because trivially, dividing by 2 is going to be the biggest proper factor. Dividing by 3 is going to be the next biggest. And we know that dividing by 6 is a possibility. So anything else has got to be better than dividing by 6. So the only possibilities are dividing by 4 or dividing by 5. I feel as though, again, I'm reaching a conclusion that I might have reached a very long time ago if I'd been a bit more sensible about it. But again, no serious harm done. So let's look at these cases. So what I'm interested in is to know whether the multiplicity of 6 goes down or anything like that, or we sort of, if it's not a fixed point. So in the first case, we have that 6 is supposedly dividing 5m plus 3m over 2, which is what? That's 13m over 2, that number 13 coming in. So 12 divides m. Which meant that it's not a fixed point, but that's not necessarily a problem. And the 13 is sort of not important, but I mean, what I mean is that 13, the effect of this 13 is just going to be that everything multiplies by 13, including the sizes of the largest factors. But the division by 2 is sort of significant. Let's just keep going. So that was the first case. If D3 is 3m over 2, we get 13m over 2. In the second case, we get 6 divides 5m. I should get this 31 thing, plus 6m over 5, which equals 31m over 5. So 5 divides m. And in the third case, I just get 6 divides 6m, which is absolutely fine. So we know that I'm going to summarize what I now know. So if 6 does not divide m, then fm is less than m, and 6 does not divide f of m. And so in that case, we're in great shape. If 12 divides m, then fm equals 13m over 2. And if 12 does not divide m, so that the 12 takes the priority over the 5 because 4 is smaller than 5, and 5 divides m, then fm equals 31m over 5. And just a little extra lemma, which is that f of 13r equals 13 times f of r, because the only primes that can be involved when we take the 3 largest divisors, if we've got a multiple of 6, are going to be 2, 3, and 5. And similarly, f of 31r equals 31 f of r. So this multiplication by 31 is something that we can sort of quotient out in a certain sense, and the same with the 13. So in order to end up with a fixed point, what we need is that as we divide by 2 here, and in brackets multiply by 13, we will eventually end up at a number that is a multiple of 6, but not a multiple of 5, or a multiple of 12. Well, dividing by 2, if we start with a multiple of 6, if we keep dividing by 2 until we hit something that's not a multiple of 12, and if we've still got any 5s in there, we'll divide those out. Okay, fine, it'll keep multiplying by 31, but that's not a problem. And until we've got rid of all the 5s, and then we'll have something that's a multiple of 6. So it looks as though we have now solved the problem. So what are the possible AIs? So I think A1 is looks as though it's any multiple of 6. That's a bit... I'm going to test that. I seem to have it. I'm going to test it in 2 ways. Now, what's gone wrong here? What about 30? I thought 30 was already a counterexample. So what happens to 30? It goes to 15 plus 10 plus 6, which equals 21. And now we're in trouble. So what have I... Ah, so that equals, sorry, 31, not 21. But I don't seem to have multiplied by 31 over 5. Multiplied by 31. Oh, 31 over, yes, okay, 31m over 5, but compared with 6m, okay. So I should have said 13m over 12 and 31m over 30. That's better. Yes, I was confusing m with n. I mean, m with 6m, so to speak. So if 12 divides m, then we divide by 12. And so we do not want, when we divide by 12, to end up with a non-multiple of 6. So if we keep on dividing by 12 until we don't have a multiple of 12 anymore, we still want to have a multiple of 6. So what numbers have that property? There will be numbers, we need that the number of powers of 3 that divide our number is strictly greater than the number of powers of 2 that divide a number, I think. Oh no, what better than that? We need a bit. So let's take our number a equals, we write it in the form 12 to the r times b. So where b is not a multiple of 12, so we need 6 divides b. And so that tells us that so that's, we rewrite that as 2 to the 2r times 3 to the r times b. So if we've got a number of the form 2 to the u times 3 to the v times c, where c is not a multiple of 2 or 3, then we'll need that by the time we've run out of the, so we'll certain we don't want to run out of the 3 powers first, so we must run out of the 2 powers first, and when we do, we must end up with still a number 1. So we have to sorry, that's well, c is not a multiple of 4, and it's not a multiple of 3, but it must be a multiple of 2. So we need that, so that should have said s. So we need r is less than s, and 2 divides c. So we have a number, we've got to have a number of the form, basically 2 to the 2r plus 1 times 3 to the s times c, where Now 2 doesn't divide C, 3 doesn't divide C, and S is strictly bigger than R. So now when we get down, we'll be able to divide by 12 R times, which will get us down to 2 times some power of 3 times something that's not divisible by 2 or 3. But we're not yet finished, because we will also be dividing by potentially by multiples of 5. And each time we divide by a multiple of 5, so let's write C equals 5 to the t times, I've already used a d, so I'm going to be safe and call it e. So now when we divide by 30, we're going to keep on subtracting and subtracting. So the first round is going to take us down to 2 to the 2 times 3 to the s minus r times 5 to the t times e dash. So the e dash I've kept on multiplying by 13 as I was dividing by 12, but that's not so important as I keep saying. And next, the next round is going to be a little bit it looks as though it's problematic. If I now multiply by 31 over 30, I'm going to lose this factor 2, and that's going to kill me off. So I now think that we also need t is equal to 0. So let me just argue that a little bit more carefully. So my argument is that for as long as the number is divisible by 12, then when we apply f, we are going to multiply by 13 over 12. So like it or not, we are iterating the process of multiplying by 13 over 12. When we multiply by 13 over 12, if we want to end up with a multiple of 6, the best that we can do is to end up with a multiple of 6 that's not a multiple of 12, so it only has one 2 in its prime factorization. If we're now still left with a 5 and a 3, well, it's particularly if we're left with a 5, then we're into sort of the second type of f, which is the one that multiplied by 31 over 30. But if we ever multiply by 31 over 30, we lose that precious factor of 2. Now we have something that's not a multiple of 6, and now it just decreases, and that's not possible. So I think the final answer, it's taken me rather a long time, but the aim here is not so much speed as just trying to display the problem-solving process. Final answer is that a equals 2 to the r, I'm going to write it like this, 2 to the 2r plus 1 times 3 to the s times c, where none of 2, 3, or 5 divides c, so I'll write that in a concise way as the highest common factor of c with 30 is 1, HCF. And also I needed that s is greater than or equal to r. And also they're both greater than or equal to 1. What do I mean by greater than or equal to 1? What if r is 0 and s is 1? That seems to be possible, so something has gone a bit funny. I think I need S. I've got that wrong. S is greater than R is greater than or equal to 0. So that way, when I keep subtracting two R's, I mean, keep subtracting 2 from this and 1 from this, by the time this gets to 0, this has not got to 0, and I'm still left with a multiple of 6. And just for fun, as a kind of last-minute check, let's just come up with some other example of such a number that's sort of not particularly obvious. So I'll take R equals 1, so that means 8 times so S has to be bigger, so I'll go for 9. I'll just leave it like that. So equal, oh, that was 72. So that was the example I had before. This is the simplest example, which is quite promising. I'm not sure that I'm going to be able to tell you what, I'm going to multiply it by 5 and see if that turns out to be a non-example, as this answer would require. So what are the, if I apply f to that, I'll get 4 times 9 plus times 5 plus, so that's divided by 2, plus 8 times 3 times 5 plus, and I can also divide it by 4, so 2 times 9 times 5, which is something times 5. So we have 36. 4 times 9 plus 2 times 9 is 6 times 9 is 54. 54 plus 24 is 78 times 5, which is sort of what we expected. It's just everything multiplied by 5. And then that's going to turn out not to be a fixed point, I believe. So the 3 largest factors of this will be 39 times 5. That's dividing by 2. Divided by 3, we have 26 times 5. But now the next biggest one is not dividing by 4. So it must be divided by 5. So that's plus 78, which is 39 times 2. So we get 13 times 3 5s plus 2 5s plus 3 2s. So 15 plus 10 is 25 plus 6 is 31. 13 times 31. And that has, well, that's not a multiple of 6, so that should give us serious problems. Let's just go to, that goes to 31 plus 13 plus 1, which shouldn't be a multiple of 6, otherwise everything's gone horribly wrong, but it doesn't seem to have, because that gives us 31, 44, 45. What are the largest factors? Well, that's odd now, so everything's going to be odd from now on, and it's going to go down. Oh, we need it to go down, so let's just verify that it does go down. Again, just as a sort of check of it, that everything wasn't nonsense. So the largest factors of that are 15. That's dividing by 3. I can divide by 5 and get 9. And I can divide by 9 and get 5. I think that's going to be my best bet. That's 2029, which has indeed encouragingly gone down. And 29 is a prime number, so we don't have 3 largest factors. So I think we've got to the moment of truth stage. After a long, long journey, I'm going to have a quick look to see if there's a written answer somewhere online. And whether that, I feel I'm not 100% confident that that's going to agree with my answer, but I don't really want to spend a lot more time checking. So this was problem 4. Just has a video solution. Sorry about this noise.
Some cities you've heard of.
Right. Let's just
Hello everyone, welcome back to Jerkin Cards, and today
I'm skipping to the end. It says write n equals 2 to the a, 3 to the b, m. So I'm trying to skip to the end of the video to see whether. So the answer is it's all numbers of the form 6 times 12 to the k times m, where k is greater than or equal to 0, 2 doesn't divide m, and 5 doesn't divide m. And I'm pretty sure that that is equivalent to my answer. So without further ado, I shall just say at that stage, I seem eventually to have got to the answer. It was a more interesting question than I at first thought, just because I made a slight sort of slip up on, I temporarily forgot what the question was asking. And probably the amount of time I took on it, given that it's supposed to be the easiest question on paper 2, would not have served me all that well if I'd actually been competing in the IMO, although I would have spent less time sort of chatting about what I was up to, so perhaps that would have sped me up a bit. Anyway, thank you for watching if you've got this far, and here I shall stop.